Alright, so another look at populations. We're now going to look at population growth. So one of the populations which has shown an expansive growth in the United States has been deer, since we removed a lot of the predators, and humans make a lot of great habitat for deer. So we'll talk about the different types of growth, but we're going to start with geometric growth, which is really not really realistic, but a good place to start with. Then we'll talk about exponential growth, logistic growth, population, and limits to population growth, including density dependent and density independent growth. Alright, so geometric growth is where the generations do not overlap, and so this can be modeled, geometrically, right? So this might occur if you have in annual plants where they grow for 1 year and then they let their seeds down, and then the next year there's another generation. So it's basically going up in steps. Each year you have more added to the population. And the equation for it is the population at a certain time is equal to the N aught, which would be the original population, the initial number of individuals times the geometric rate of increase. So if it goes up by 50 individuals per year, that would be the lambda. Switch that, and then t is the number of time intervals for that generation. All right, exponential growth is similar, except you have overlap between the generations. So this is continuous population growth in an unlimited environment, so there's no restrictions to the growth. So it's an exponential growth. Okay, so this is the change in the population over time equals the rate times the population. So this is appropriate for populations, again, with overlapping generations. As population size increases, the rate of population increase is as well. Okay, but exponential growth on populations at any time, so if you're including the time component, you're going to have more variables. So the number of individuals in sub t at a certain time. N aught is the initial number of individuals. E is the base of natural logarithm, so it is a standard number. Times the R max, the per capita rate of increase, and then t equals the number of time intervals. Okay, so an example of a exponential growth would be the Eurasian collared duff, which we talked about last time, and its dispersion into a new area. As it disperses into a new area, it initially starts really low, but eventually starts to grow at a greater and greater rate. So this is not realistic, though. At some point, the exponential growth is going to have to level off, and that's what logistic population growth is. So as resources are depleted, the population growth rate slows and eventually stops. Okay, and this creates this sigmoid or S-shaped population growth curve. And the point at which it levels off is called the carrying capacity, which is the finite amount of resources in an environment, and that's what controls the population. Okay, so again, this is what it looks like. This will occur in small paramecium or one-celled organisms. If you give them a medium, they will continue to grow and grow and grow until they run out of that medium. They run out of their nutrients and supplies, and then they will level off. Alright, so the equation, the R max, the per capita rate of increase under ideal conditions, so that's the exponential growth rate basically. And as the population nears k, the right side of the equation starts to near 0. So that means the rate of increase will also decrease. As population size increases, the logistic growth rate becomes a small fraction of the growth rate. So as you get higher and higher, closer to carrying capacity. The highest rate of growth is k divided by 2. So in this area here, you have exponential growth rate occurring. And N divided by K is called the environmental resistance. Okay, and so as you get closer to carrying capacity, you are going to have a higher environmental resistance. So limits to population growth include environmental limits, and the environment is composed of abiotic and biotic factors. So there's density-dependent factors, which usually include things like disease or competition among other living organisms. And an example I have of that is white nose syndrome in bats has been a very limiting density-dependent factor. Because these bats are clustered, they get this disease, they all get it, and then they can die. And then you have density-independent factors where it doesn't matter how many are in an area, they can all get wiped out or increased. Or they can also increase their population in a good year. So this is examples of this include natural disasters or weather. So if you have a really good, nice, warm, moist year that's ideal for population growth, you'll have a boom. If you have a natural disaster come through and like a fire or something deplete all the resources, then you could have a bust year. So some examples of some density independent factors, Bogue and Grant. We're looking at a finch. There were about 1,200 of them. After this drought in 1977, the population fell to 180, so almost just over 10%. The food plants failed to produce seed crop, and in 1983, 10 times the normal rainfall caused population to grow. So again, this is independent factors. These are these are weather patterns, drought, and increase in rain, which caused a bust and a boom. There are also another researchers, Grant, documented several ways finches utilize cacti. They found that they open flower buds in dry season, eat the pollen. They consume the nectar and pollen from mature flowers. They eat the seed coating. They eat the seeds. They eat insects from rotting cactus pads. So a lot of these are density-dependent factors because they are also destroying the ability of the cactus to reproduce. And if they do that, then they're going to destroy their resources and cause a population decline. So finches tend to destroy the stigmas, and so they can't be fertilized, so they can't disperse and grow. Wet season activity also may reduce the available to finches during the dry season. So if they're destroying the reproductive structures, that's a density-dependent factor. The wet season activity would be density-independent, weather-related. This cactus is the main source for the cactus finches, which is negatively impacted by El Nino, which was a climatic event, density-independent. The stigma snapping also delayed the recovery, which is density-dependent. And so you have this interplay of biotic, which is generally density-dependent, and abiotic factors, which are density-independent.